Hello. In the previous lecture, we proved the fundamental theorem of Galva theory, and we've seen some applications of the fundamental theorem of Galva theory. In today's lecture, we are going to start with a proof of the fundamental theorem of algebra. So what does it say? So it says that if I start with a non-constant binomial with complex coefficients, then it has a complex root. So that's the statement of the fundamental theorem of algebra. And let's see how what we proved about Galva theory can help us to show this statement. Suppose to the contrary that I can find some polynomial with complex roots that does not have a complex zero. So, suppose to the contrary that there is a complex polynomial that has no complex zeros. And now I'm going to add zeros to complex numbers to get something larger. That means let E be a splitting field of this polynomial over complex numbers. But it's much easier to work with real numbers. So what we do, we take a normal closure of E over R, not there, but rather a normal closure of E over R. If you don't remember the main properties of normal closure, let me just mention that here what we need from L is that L over R is a finite extension, L over R is a normal extension, and L contains E. These are the three properties that we need over here. So again, let me summarize them. So L over R is a finite extension. And E is contained inside L. Therefore, all the zeros of F and complex numbers, both of them, are subsets. So complex numbers is a subset of L, and all the zeros of F are inside L. And L over R is a finite normal extension. Okay, so these are the properties that we need in this proof. When we say it's a normal closure, it means that with respect to these properties, it's one of the smallest choices. So meaning that inside L, we don't have any subfield with the same properties. Okay, we have proved the existence of such extension and so on. We don't want to repeat that argument. If you don't remember it, that's fine. You can go and look at the lecture notes and make sure that you know how to prove that statement. For now, assume that we have such an extension, and let's continue with the argument. Now, the other thing that we want to point out that this extension L over R that we know is a normal extension is indeed a Galva extension, because characteristic of R is 0. Every non-constant polynomial is separable, and therefore L over R is a separable extension. This you had in your homework assignment as well, but let's discuss, see why this is the case. It's not very hard. Let's see why this is the case. The point is that when I give you an irreducible polynomial, it is separable if and only if it does not have multiple zeros, and a polynomial does not have multiple zeros if and only if it is coprime with its derivative. But when I start with an irreducible polynomial, it is always coprime with a polynomial of 1 less degree. So from there, you deduce that the extension L over R is a Galva extension, is a finite Galva extension. Okay? Now, Galva taught us that it's a good idea to think about the symmetries of the field extension. So let G be the symmetries of the field extension L over R. Now, here is the main trick of the argument that you will soon see why it is relevant and how it can help us. Let P be a CELU 2 subgroup of this group of symmetries. I know it is kind of all of a sudden and not clear why we are considering such a subgroup. But as I have pointed out, you will see why we have to consider the CLU2 subgroups rather soon in the next line. So let P be a CLU2 subgroup of the group of symmetries of this group G. And let K be the set of fixed points of P. Now let's recall what the fundamental theorem of Galva theory tell us about the field K. By the fundamental theorem of Galva theory, we have that the index of G over P, the index of the subgroup P inside G, okay, what number is it? So here is actually where the CLU2 subgroup comes to the picture. When P is a CLU2 subgroup, the cardinality of P is a power of 2, and the index of P in G is an odd number. So the cardinality of P is supposed to be the largest power of 2 that divides cardinality of G. Therefore, index of P in G is an odd number. That's why we use the fundamental theorem of Galva theory and start with looking at the index of P inside G. So index of P in G is an odd number, and fundamental theorem of Galva theory tells us that it is the same as the field extension, as the index of the, or the degree of the field extension, fixed P over fixed G. The fixed points of G, the group of automorphisms of the extension, the Galois extension R over L over R, because it's a Galois extension, is exactly R. And the fixed points of P, we call it K. So altogether we get that K is an odd degree extension of the field of real numbers. Now, why is that relevant? You see, so we use the CLU2 subgroup to get an odd degree extension of real numbers. Why is odd relevant? Because when I give you an odd degree extension, all the intermediate subfields are going to be of odd degree as well. That means what? That means for every alpha inside this field, when I look at the minimal polynomial of alpha over the real numbers, I get a real polynomial that is of odd degree, because the degree of this polynomial is the degree of the intermediate field extension R bracket alpha over R, which divides the degree of K over R, and that one is an odd number. So we end up getting an irreducible polynomial that is of odd degree. But we don't have such a thing unless it's of degree 1. That's why we wanted to get an odd degree extension of real numbers, because there is no such extension except the real numbers themselves. Again, let's go over the argument, because every alpha that I give you inside this field extension, the degree of the minimal polynomial of alpha over the real numbers is the degree of the field extension that's given by R bracket alpha over R, and that should divide the degree of the K over R, which is an odd number. So that means I'm getting an irreducible polynomial over R bracket X that has odd degree. And my claim is that that's not possible. Why is that the case? We've seen this, we have argued this actually in the previous course where we said that every odd degree real polynomial has a real root. Let's quickly go over that argument. When I give you an odd degree real polynomial, then I can let x, my variable, go to plus infinity, or let's say t, my variable, let's go to plus infinity. And if the leading coefficient is a positive number, then g of t goes to plus infinity. And when I let t go to infinity, negative infinity, when the leading coefficient is positive, g of t goes to negative infinity. Now I can use the intermediate value theorem. At some point it's plus infinity, at some point it's negative infinity, so it should meet the x-axis in the middle at some point. That means that at some point the value of g should be 0. If the leading coefficient is negative, then as we let t go to plus infinity, the value goes to negative infinity. And then when we let t go to negative infinity, it goes to plus infinity. Again, I can use the intermediate value theorem and deduce that g has a 0, but an irreducible polynomial of degree at least 2 cannot have a 0. And that tells us that this field K, that was the fixed points of the CELU2 subgroup, is just real numbers. Again, K is the set of fixed points of P, and R is the set of fixed points of G. Because they are the same fields, the groups should be the same. That means G is P, but that means G is a 2 group. The number of elements of G is a power of 2. Now, if the number of elements of G is at least 4, again, before I go there, let's recall the CELU2 subgroup. The first CELU theorem tells me that if 2 to the k divides cardinality of a group, then this group contains a subgroup of order 2 to power k minus 1, 2 to power k minus 2, 2 to power k minus 3, and so on. So CELU theorem, the first CELU theorem, guarantees existence of these 2 subgroups inside any finite group. So if I give you a finite group that its cardinality, if I give you a finite group and I tell you 2 to power k divides the cardinality of this group, then CELU theorem guarantees existence of a chain of subgroups of this group that have cardinality 2 to power k minus I, as I ranges from 0 to k. Now I pick only the top 2 elements, assuming that my group has at least 4 elements. If k is at least 2. If k is at least 2, then I can pick these top 2 groups, G1 and G2. And I get a subgroup G1 that has index 2 and a subgroup G2 that has index 4. If I again use the fundamental theorem of Galva theory, I deduce that the field of fixed points of G1 is an extension of real numbers, and the degree of this extension is 2, and the degree of the extension of the fixed points of G2 over the fixed points of G1 is again 2. Okay, now let's start with fixed points of G1. Because fixed points of G1 is a degree 2 extension of real numbers, every alpha that's not inside real number and inside this field is enough to generate the entire field. That means that fix of G1 is just R square bracket alpha. And moreover, the minimal polynomial of alpha is of degree 2. So I get a quadratic polynomial over real numbers with no real root because it's supposed to be irreducible. Okay, so now when I give you a quadratic degree 2 polynomial with no real root, we know that that implies it has 2 distinct complex roots. That means this R bracket alpha is indeed isomorphic to complex numbers, because I can use this complex root and add it to the real numbers and get an isomorphic field. So the fixed points of G1 is indeed isomorphic to the field of complex numbers. And because fix of G2 is a degree 2 extension of fix of G1, that means what? That means I can find a degree 2 extension of complex numbers. So if I give you the degree 2 extension, whatever it is, let's call it maybe, the name doesn't matter. So if beta is an element of this degree 2 extension, that means what? That means, so there exists beta such that when I add it to complex numbers, I get a degree 2 extension. And that means the minimal polynomial of beta over complex numbers is of degree 2. And it is irreducible over complex numbers. Let's call this polynomial to be this one. So x squared, all together we end up getting a polynomial of the form x squared plus ax plus b over the complex numbers, which is irreducible in complex numbers. And that's the same as saying that which has no complex root. But that's simply not possible. Every quadratic equation over complex numbers does have a zero. Let's see why. Let's see why this is the case. Suppose that I give you this quadratic equation, x squared plus ax plus b. I just use the completing the square method, and I end up getting that it is x plus a half squared, and that would be a squared divided by 4 minus b. And this is a complex number. A squared over 4 minus b is a complex number. So I can use the polar coordinates for this complex number. That means this magnitude times the amount of rotation that's needed to reach to this complex number. So r times e to the power I theta. That's the polar coordinates of the right-hand side of this equation. Now I'm looking for some complex number whose square will be, so I'm looking for some complex number whose square is going to be r e to the power I theta. That is square root of r times e to the power I theta half. Because when I square this guy, I get r e to the power I theta. So altogether, we get that this number, square root of r e to the power I theta half minus a half, coming from this point, is a zero of x squared plus ax plus b in complex numbers. And that's a contradiction. That tells me that there is no such irreducible polynomial. So I get this contradiction that I claimed over here. So altogether, I mean, what does this contradiction even mean? This tells me that it's not possible for G that has cardinality 2 to the k. It's not possible for k to be at least 2. K should be at most 1. And that means the cardinality of the group G is at most 2. But remember, G is the group of automorphisms of the field extension L over R, and L over R is a Galois extension, so that's the same as cardinality of the group G. So the degree of the extension L over R is either 1 or 2. It cannot be 1 because L contains complex numbers. So it should be 2, and L is the set of complex numbers. But remember, L contains all the zeros of the polynomial f that was supposed to have no zero in complex numbers. And there it is. That's my contradiction. Because f was supposed to have no zero in complex numbers, all the zeros of f are inside L. L is the set of complex numbers. So that means all the zeros of f are in complex numbers. That's a contradiction, and that finishes the proof. Okay, so we managed to prove the fundamental theorem of algebra. There are many proofs for this result, including some proofs using complex analysis and nice proofs using complex analysis. But this proof was also pretty interesting because the only facts from analysis that are used here are the fact that every odd degree polynomial, every odd degree real polynomial has a real root, and every degree 2 polynomial over the complex numbers has a complex 0. So these are the only two facts that are used in this proof. Okay, so next, what we want to show, what we want to find out is we want to pinpoint exactly when the number of intermediate subfields is finite. Okay, so this is what we want to show. In the previous lecture, we've seen that this number of intermediate subfields is finite when E over F is a finite separable extension. So if E over F is a finite separable extension, then there are only finitely many intermediate subfields for E over F. Now we want to find out exactly when this phenomenon happens. The next theorem tells us that when E over F is a finite extension, then the number of intermediate subfields is finite precisely when E can be generated by a single element over the base field. So if I can find some alpha and generate E by F and alpha, then I can deduce that the number of intermediate subfields is finite and vice versa. Before getting into the proof, let me introduce some notation that are going to be used later on. So first thing is that if I can generate the larger field using an element alpha, a single element alpha, and the base field, then I call alpha a primitive element. So again, alpha is called a primitive element if the smallest subfield of E that contains both the base field and alpha is the entire field E. So if this is the case, then in fact we denote E by F parentheses alpha, and we call alpha to be a primitive element. Here I'm not assuming that E over F is an algebraic extension. It can be any field extension. So if alpha over F is algebraic, then we've seen that it's enough to evaluate polynomials over alpha and end up getting a field. Therefore, I do not need to put parentheses around alphas. But when alpha over F is not algebraic, F parentheses alpha can be viewed as the field of rational functions evaluated at the point alpha. When alpha is algebraic over F, it's the same as looking at the ring of polynomials evaluated at alpha. But in any event, such an alpha is called a primitive element of this field extension. And this field extension in that case is called a simple extension. So then we say E over F is a simple extension of if we do have a primitive element. And we often refer to this result, to this theorem over here, as the primitive element theorem. Okay, so let's go to the proof of this result. This is an if and only if statement. Let's start by going from left to right. So I'm going to assume that there are only finitely many intermediate subfields in the field extension E over F, and I want to show then E is generated by F and some element alpha. Okay, I'm going to proceed by a strong induction on the index of this field extension. Knowing that there are only finitely many intermediate subfields between F and E, there are only finitely many of them, I can go up, up, up till I cannot go further. That means I can find some intermediate subfield K, which is maximal among proper subfields. which means there is no other proper subfield that is above K and below E. So that means the set of intermediate subfields of the field extension E over K has only two elements, either E, the larger one, or the smaller one, K. And K is proper, is not the entire field. So again, this condition is the same as saying that K is maximal among proper subfields of E. We do not necessarily have such subfield, but when I'm told that there are only finitely many intermediate subfields, we can immediately deduce that there is such a maximal proper subfield. And because it's a proper subfield, we deduce that the degree of this field extension is strictly less than, using the Tower rule, it's strictly less than the degree of the field extension E over F, and therefore I'm allowed to use the strong induction hypothesis. Notice that the set of intermediate subfields of K over F is definitely a subset of the intermediate subfields of E over F. Knowing that intermediate subfields of E over F is a finite set, we deduce that the set of intermediate subfields of K over F is also a finite set. And so I do have the hypothesis for the strong induction. So I am allowed to use the strong induction hypothesis for the field extension K over F and deduce that K is F bracket beta for some element beta. So again, that means that K over F does have a primitive element beta. Now, because there is no other field above K and below E, if I pick something outside of K and add it to K, I have to end up getting the entire field because there is no other intermediate subfields between K and E. K is a maximal proper subfield. Again, because K is a maximal proper subfield, we deduce that for every element outside of K, inside E, when I add it to K, I get the entire E. Okay? There is nothing in between. See, if I add something outside of K, I get the entire field. Altogether, we deduce that if I add beta and K to the base field F, I get the entire field E. Okay, not bad. So I use the induction hypothesis and deduce that I can generate E by the base field F and two elements. Now I want to change this 2 to 1. Let's start with assuming that F is a finite field. In that case, actually, there is not much to discuss. Let's see why this is the case. If F is a finite field, because E over F is a finite extension, E is also a finite field. And therefore, the multiplicative group of E, which is all the elements of E minus 0, is a cyclic group. This is what we have proved before. So the multiplicative group of every finite field is a cyclic group. So say the multiplicative group of E is generated by alpha. Now, when I add alpha to the base field F, I am going to get all the powers of alpha inside this set. So I'm going to get the entire field E. So alpha is also a primitive element of this field extension. So then we are done. So if F is finite, we are done. So from this point on, I'm going to assume that F is infinite. So F is not finite. So that's going to be my assumption from this point on. Now, my claim is I can find some element inside this field that is infinite and make sure that beta plus C gamma is a primitive element, which means E is generated by F and the element beta plus C gamma. Okay, let's see how the proof goes. I start with F. To every element of F, I assign the field that I proposed up there, which means that's generated by beta plus C gamma and F. So this field would be an intermediate subfield of the field extension E over F. But remember, by assumption, the codomain of this function is a finite set. This codomain is a finite set. If and f is infinite, again, we assume this. So the domain is infinite, the codomain is finite, so at least one of the fibers, one of the elements inside the codomain, so at least for one of the elements inside the codomain, there are infinitely elements that are mapped to that intermediate subfield. Again, let's think about it. I have finitely many points. I'm mapping infinitely many points to them. So then infinitely many of them are mapped to the same point. So that means what? I can find C1, C2, ... In fact, infinitely many is not that important for me. It's enough to find 2, and that's enough for me. So there are infinitely many pairwise distinct elements, C1, C2, ... and so on inside F, such that all of these CIs are mapped to the same fields, so to the same intermediate field. So there exists these C sub i's and some intermediate subfield L, such that all of these C sub i's are mapped to the same intermediate subfield L. So L is the same as the field generated by F and beta plus C sub I gamma, no matter what I pick. For every I have this equality. In particular, beta plus C1 gamma and beta plus C2 gamma, both of them are elements of the same intermediate subfield. And therefore, their difference belongs to the same intermediate subfield. But the difference, betas cancel out. I get C1 minus C2, which is a non-zero element of F. And so it's a unit inside F, times gamma. This belongs to L. But remember, as we just said, C1 minus C2 is invertible and it is inside L. So this part is already inside L. The product is inside L, and this guy is inside L, and it's non-zero, so its inverse is also inside L. L is a field. So I can cancel out, and from there we deduce that gamma is inside L. So this part, this should be inside L as well. Now that gamma is inside L, remember all these elements were inside L, and gamma turns out to be inside L as well, and therefore beta should be inside L as well. So again, beta plus C1 gamma is inside L. C1 itself is inside L. Gamma is inside L, and therefore beta is also inside L. So beta turns out to be inside L. So both beta and gamma are inside L. F is also a subfield of L. Therefore, the field generated by F, beta, and gamma is a subset of L. But remember, the field generated by F, beta, and gamma is the entire field E. There it is. Over here. Where is it? Over here. So altogether, we deduced that this L, where infinitely many of these C sub i's give me this intermediate subfield, is indeed the entire E. Therefore, E is generated by this element beta plus C1 gamma. In fact, for infinitely many C sub i's, I can get the same equality. Therefore, I get this equality. That's good. So this implies that the left-hand side implies the right-hand side. Now, let's assume that my extension is a simple extension, and I want to show that there are only finitely many intermediate subfields. Now, the trick is to consider this function. From the set of intermediate subfields, so given an intermediate subfield K, I'm going to give you a polynomial, a monic polynomial in E bracket X. So how am I going to do it? I take this intermediate subfield, and then I consider the minimal polynomial of alpha, this alpha that generates E, I'm going to consider the minimal polynomial of alpha over this intermediate subfield. And that would be a polynomial in K bracket X, but K is a subset of E, so I get a polynomial in E bracket X. So now I'm giving you a function from the set of intermediate subfields E over F, two set of polynomials, monic polynomials in E bracket X. Now, the key property of this function is the following. So this function has two key properties. We will show that this function is injective, and we will show that image of G is finite. From these two assertions, we deduce that the domain of this function is also a finite set. And that's exactly what we wanted to show. So again, we are going to show two assertions. Image of G is finite and G is injective, and deduce the domain is finite, and finish the proof. Okay, so let's start with showing that image is a finite set. Okay, so how do I do it? The point is that for every intermediate field that you give me, the minimal polynomial of alpha over F, the smallest one, is inside F bracket X, but F is a subset of K, and therefore I can view this as an element of K bracket X. So the minimal polynomial of alpha over F is a polynomial in K bracket X, and it does have alpha as a 0. And so the minimal polynomial of alpha over K should divide this. So this is precisely G of K. So no matter what K I pick, G of K ends up being a monic divisor of the minimal polynomial of alpha over F. So the minimal polynomial of alpha over F is a fixed polynomial, and then all of these GKs that we are going to get are going to be monic divisors of this polynomial, and there are only finitely many monic divisors of a given polynomial. So that's why image of G is a finite set. So again, I have that G of K divides is a divisor of the minimal polynomial of alpha over F. So image of G consists of divisors, monic divisors of the minimal polynomial of alpha over K, and therefore image of G is finite, consists of finitely many elements. Now, if I show G is injective, we get that the domain of G should be finite as well. So let's assume that G of K1, an intermediate subfield, is equal to G of K2, another intermediate subfield, and I want to argue that K1 is equal to K2. Suppose these GK1 and GK2, these are polynomials, monic polynomials in E bracket X. Suppose that these polynomials, the coefficients are given by E sub I. So it's x to power m plus E sub m minus 1, x to power m minus 1, and so on. Remember, G of K1 is the minimal polynomial of alpha over K1. And G of K2 is minimal polynomial of alpha over K2. So this means these coefficients, E sub i's, belong to both K1 and K2. So E sub i's are in both K1 and K2. Therefore, if I start with F, the base field, and add these coefficients, E sub 1, E sub 2, E sub m minus 1, to the base field, and call this field K, this would be a subfield of K1 and K2. So this K is a subfield of K sub i's, no matter what index I pick. First. Second, this polynomial that's equal to G of K1 and G of K2, this belongs to this smaller field, K bracket X. In fact, that's how we chose K. We chose it in a way that contained that this polynomial belongs to K bracket X. Remember, alpha is the 0 of this polynomial. So alpha That means the minimal polynomial of alpha over k should be this one, but at least I can say that the minimal polynomial of alpha over k has degree at most m. Okay, now let's consider the degree of the field extension E over k. This degree of the field extension E over k is, remember, when I add alpha to f, I get the entire field E. Therefore, when I add alpha to a slightly larger field that we call k, still I'm going to get E. So E is nothing but k bracket alpha. This statement is true for every intermediate subfield k. I'm going to use the same statement for k sub i's as well. So k bracket alpha is E, and therefore the degree of E over k is the same as the degree of k bracket alpha over k, and that is the degree of the minimal polynomial of alpha over k. As we just discussed, because alpha is a zero of this polynomial that has degree m, I can deduce that degree of the minimal polynomial of alpha over k cannot be more than m. Remember that this is a polynomial inside k bracket x. Okay, so far so good. We understand that the degree of this field extension cannot be more than m. But on the other hand, using the Tower rule and using the fact that k is contained inside k sub I can argue that the degree of this field extension is like product of the degrees of the field extensions E over k sub I and k sub I over k. Then degree of the field extension E over k sub I, by the same argument as we did just right now, is the same as the degree of the minimal polynomial of alpha over k sub i's. But that we know to be these polynomials, therefore the degrees would be m. So the first factor is going to be m. The second factor is, of course, an integer that's at least 1, a positive integer. That means that this product is at least m. At the same time, this number is at most m. So this means that all these quantities are equal. In particular, I deduce that the degree, this factor over here should be 1. It cannot be more than 1. If this guy is more than 1, then the bottom side is going to be at least 2m, but it's supposed to be at most m, and that gives us a contradiction. So therefore, k sub i's are k, no matter what index I pick. So k1 and k2, both of them are k. In particular, they are equal. That implies that G is injective, and that finishes the proof. So again, we proved that the number of intermediate subfields of E over F is finite if and only if E over F is a simple extension. Remember, for finite separable extensions, we have already proved that there are only finitely many intermediate subfields. That means that we showed for a finite, every finite separable extension is a simple extension. Every finite separable extension is a simple extension. In some textbooks, this proposition is referred to primitive element theorem. So in some textbooks, primitive element theorem is mentioned only for finite separable extensions. Now we deduce this statement using this if and only if statement that there are only finitely many intermediate subfields if and only if the extension is a primitive extension. For finite extensions, we prove this, and therefore we deduced that a finite separable extension is always a simple extension. Again, let's quickly go over the argument. Because E over F is a finite separable extension, the number of intermediate subfields is finite. We proved this first for Galva extension using the fundamental theorem of Galva theory. And for an arbitrary finite separable extension, we considered a normal closure of this extension, and we argued that a normal closure of a separable extension is always normal and separable. and therefore it's always a Galva extension. So that was how we proved this statement, that a finite separable extension always have finitely many intermediate subfields, and using in combination with the previous result, we deduce that E over F is a simple extension. Okay, so it's clear that understanding the separability criterion is quite important and useful. So next, we are going to focus on separability criterion, and we are going to see if we can put together all the elements that have separable minimal polynomials and end up getting a subfield. We use this later in order to investigate towers of separable extensions. Okay, so let's start with some of the results that you have already seen in your homework assignment. So let's go through the argument and see what we need to prove and so on. So I want to understand when E over F is a separable extension. Let's recall that an extension is a separable extension, an algebraic extension is a separable extension whenever, for every alpha inside the larger field, the minimal polynomial of alpha over F does not have multiple zeros, or does not have multiple zeros in its splitting field. And we have proved, we have used the formal derivatives of polynomials in order to understand whether or not a polynomial has multiple zeros in its splitting field or not. We showed that a polynomial g in f bracket x does not have multiple zeros in its splitting field if and only if the GCD of g and its derivative is 1 in f bracket x. Okay, now let's try to use this for an irreducible polynomial, because the minimal polynomial of alpha over f, after all, is irreducible. So now this is the question that I'm trying to understand. If g is an irreducible polynomial, what can I say if it's not separable? Or alternatively, under what conditions an irreducible polynomial in f bracket x is going to be a separable polynomial? So that's the kind of question we need to understand and we need to answer. And this is a kind of lemma that you have already seen, but let's go over this. So suppose f is a field, and I give you a polynomial that is irreducible, then this polynomial is not separable in f bracket x if and only if its derivative is 0, the 0 polynomial. This is quite counterintuitive, because in calculus we have always seen that derivative of polynomial is only 1 degree less than g. So it seems that if g prime is 0, then g should be constant, it cannot be irreducible, and whatever I said is correct as long as the characteristic of f is 0. But in general, derivative of a polynomial might be 0 without g being constant. For instance, if the characteristic is p, then x to power p minus 1 has derivative equal to 0. But the polynomial, of course, is not constant. Okay, now let's again try to understand this statement. G is irreducible, then it's not separable precisely when g prime is 0. Okay, it's if and only if. We try to go with bijective, go with if and only if statements and change the format of if and only if one step at a time to get to the desired result. I'm going to go through the logic first and then summarize what we've done. Because G is irreducible, separability is equivalent to saying that it does not have multiple zeros over its splitting field, in its splitting field. Not having the multiple zeros in the splitting field is equivalent to saying that the GCD of G and its derivative is not 1. Again, okay, so again, because G is irreducible, not being separable is equivalent to saying that it has multiple zeros in its splitting field. Now, having multiple zeros in the splitting field is equivalent to saying that GCD of G and its derivative is not 1. Because G is irreducible, when I tell you a polynomial of a smaller, a polynomial like this one that has degree at most degree of G, and it divides G, then it should be some unit multiple of G. It should be the same degree because G is irreducible. So knowing that the GCD of G and G prime is not 1, this fact is going to be equivalent to saying that the GCD of G and G prime is just sum is constant times G, because G is irreducible. We have this equality. And this fact, you see, a unit multiple of G definitely divides G. A unit multiple of G is going to be the GCD of G and some other polynomial if and only if G divides the other polynomial. So this equality holds if and only if G divides G prime. But remember, degree of G prime is strictly less than degree of G. So the only multiple of G that has degree less than degree of G is the zero polynomial. So again, G is supposed to divide G prime, but degree of G prime is strictly less than degree of G. That means G prime is 0. And of course, when G prime is 0, then G does divide G prime. So altogether, this is the kind of logic that we are writing down. G not being separable is equivalent to saying that G and G prime are not co-prime. Here I'm using the fact that G is irreducible. Then again, because G is irreducible, the GCD not being 1 is going to be equivalent to saying that GCD is some unit, some constant multiple of G. That's equivalent to saying that G divides G prime. Because degree of G prime is strictly less than degree of G, that's equivalent to saying that G prime is 0. And that finishes the proof. So altogether, what we are getting is this. A polynomial, an irreducible polynomial in f bracket x is separable, is not separable if and only if G prime is 0. Or it is separable if and only if G prime is not 0. So we have an algorithmic way of understanding whether or not a polynomial is separable or not. Whether a polynomial is separable or not. Okay, so now let's see an immediate corollary of this statement. An immediate corollary is that whenever I give you a field of characteristic 0, then every irreducible polynomial is separable. Okay, so let's go through the proof. By the previous result, we know that an irreducible polynomial is separable if and only if its derivative is not 0. We can just compute derivative of G. When I compute derivative of G, I get n times a sub n x to the n minus 1. If this polynomial happened to be 0, that's equivalent to saying that all the coefficients n times a sub n, n minus 1 times n, a sub n minus 1, till the coefficient of x, all of them should be 0. But characteristic is 0. So this means when I tell you I times a sub I is 0, I can deduce a sub I is 0. Because characteristic of f is 0, an element, if I tell you I times a sub I is 0, then I can deduce that a sub I is the 0 element itself. Remember, it's a field. And so when I is not 0, then I is invertible, so I can multiply both sides of I, a sub I, by inverse of I, and end up getting that a sub I is 0. We obtain that all a sub i's are 0, and that means that the polynomial g is just a constant polynomial. It's compatible with our intuition from calculus that when derivative of a polynomial is 0, then the polynomial is the constant polynomial. But that's a contradiction because g is an irreducible polynomial. It cannot be constant. So that contradicts the fact that g is an irreducible polynomial, and that finishes the proof. So in a characteristic 0 field, all non-constant polynomials are separable, and therefore that means every algebraic extension of a field of characteristic 0 is automatically separable. So this non-separability issue is a positive characteristic issue. In characteristic 0, there is no such concern about separability. This is a great help when we study when we are studying Galva extensions, because that tells me that when the characteristic is 0, the separability condition is automatic. I only need to make sure that my extension is a normal extension. But what happens when characteristic is p for a positive number p, for a prime number p? So suppose characteristic of the field f is a prime number p, and I give you some irreducible element in f bracket x. What happens? Is it possible for this guy to not be separable? The answer is yes. Then what happens is that it's going to be some other polynomial evaluated at x to power p. So I can repeat this process and end up getting some polynomial in f bracket x that is both irreducible and separable. And what's the connection between g naught and g? G of x is nothing but g naught of x to power p to the m for some non-negative integer m. So if m is 0, g is g naught, and g is separable. But when g is not separable, then it's going to have a separable source. So every polynomial, every irreducible polynomial has a separable source. So g is g naught x to power p to the m, where g naught is irreducible and separable. So I refer to this g naught as the separable form of g. Okay, so let's see how the proof goes. This is an important corollary. We are going to use this in the later in order to understand an arbitrary field extension and see under what condition we can guarantee that it's separable and so on. Okay, so let's see how the proof of this corollary goes. So if g is separable, then as I've mentioned, I can just let g naught to be g and set m equal to 0, and there is nothing to prove. It's fine. So for separable polynomials, I'm okay. If g is not separable, though, then what does that mean? Because g is irreducible, we have already proved not being separable is equivalent to saying that g prime is 0. So if I call coefficients of g to be a sub I, so if g is summation of a sub I x to the I, then g prime is summation of I a sub I x to power I minus 1. So that means that I a sub I is 0 for every I. So if I is 0, it's already clear. Otherwise, it's one of the coefficients of g prime, and because g prime is 0, we deduce that I times a sub I is 0. If my characteristic doesn't divide I, then I is a unit inside this field. So knowing that a sub I is 0 implies that a sub I is 0. So a sub I is 0 automatically when p doesn't divide I. And remember, if p does divide I, this condition is redundant because p divides I and that p is characteristic. So I do have that equality for free. So this equality is a meaningful condition only when p doesn't divide I, when the characteristic does not divide I. So altogether, what am I getting? I'm getting that if my irreducible polynomial g is not separable, then I can write g as summation of only those terms that have indices that are multiples of p. So p0, p, 2p, 3p. So I get only those terms where the exponent of x are powers, where the power of the exponent of x are multiples of p. So if I think about it as a polynomial in terms of x to the p, so meaning if I just look at the coefficients, but then change the power of x to x to the I, and call this as a new polynomial g sub 1, the top equality tells me that this g is nothing but g sub 1 evaluated at x to the p, or plugging in x to the p for x. So all of a sudden what we are getting is that if g is an irreducible polynomial, then I can, and it's not separable, then it is g sub 1 of x to the p for some polynomial g1 with coefficients inside the same field. We also notice that this polynomial g sub 1 is also irreducible. Why is that the case? If it's not irreducible, then I should be able to write it as product of two non-constant polynomials. Let's call these non-constant polynomials h1 and h2. So I can write down g1 as h1 times h2. So now if I plug in x to the p to both sides, I get that g of x is g1 of x to the p, but g1 is supposed to be h1 times h2. Because I plugged in x to the p, I have to plug in x to the p. But the point is that because h1 and h2 are not constant polynomials, I'm ending up writing g as a product of two non-constant polynomials, which is a contradiction because g is irreducible. So altogether, what we are getting is that if g is not separable because it's irreducible, we can write down, we can find some irreducible polynomial of degree strictly less than degree of p. In fact, degree of g1 would be precisely degree of g divided by p, the characteristic. We can end up getting this irreducible polynomial so that this equality holds, so that g of x is g1 of x, so we end up getting that there exists this irreducible polynomial in f bracket x with degree less than this, and g of x is g1 of x to the p. Now we are going to repeat this again and again. Or alternatively, as always, whenever you hear the word, the phrase again and again, it should remind you of some type of induction. So we are going to proceed by strong induction on the degree of the polynomial g. If I'm in the base of induction, then it's not a multiple of p, or you can either you can use this argument where you immediately see that it has only one zero and that it has a zero inside f, so it's a separable polynomial. So in that case, we are done. Now let's go to the induction step, the important part. If g is separable, again we are done. So let's assume that g is not separable. And then by the argument that we just presented, it's going to be g1 of x to the p for some g1 that is also irreducible, and its degree is strictly less than degree of g. And so I can use the strong induction hypothesis. By the strong induction hypothesis, this g1 is g naught of x to the p to the m for some non-negative integer m and some irreducible and separable polynomial in f bracket x. Now let's connect it to g. G is g1 at x to the p. g1 itself is g naught at x to the p to the m, but now instead of x, I'm going to write down x to the p to the m, x to the p. So altogether, we get that it is g naught at x to power p to power m plus 1. So we end up finding this irreducible separable polynomial in f bracket x and write down g as g naught, this polynomial g naught, at some power of p, x raised to some power of p, and that completes the proof. That gives us a strong induction step. Okay, let's see how this can help us to understand separable elements inside an algebraic extension. What do I mean by separable elements inside an algebraic extension? So suppose I give you an algebraic extension. Then I consider the set of all the elements inside this extended field, where the minimal polynomial is a separable polynomial. If my extension is a separable extension, then E sub sep is the entire E. In fact, this is if and only if. Yeah? So E sub sep is equal to E precisely when E over F is a separable extension. Maybe it's worth writing it down. So E over F is a separable extension if and only if E sub sep is E. Okay. Now the claim is this is indeed an intermediate subfield. It is a field. I mean, this set being an intermediate subfield is a non-trivial fact. Then if we show it's a subfield, it's actually rather easy to see that this is a separable extension because every element inside this guy, the minimal polynomial, is automatically separable. So this part is immediate as soon as we show E sub sep is a separable extension, is an intermediate subfield. Next, we argue that when characteristic of F is 0, then every algebraic extension is separable, that we have already seen, and therefore for separable extensions, as we just mentioned, E sub sep is the entire E. So this part of the part 2 is actually rather easy. This part is more important. If the characteristic is positive, then for every alpha, I can raise alpha to a power of p and end up being inside E sub sep. So this separable part of E. In fact, we call E sub sep the separable closure of this field extension. So we call it the separable closure of F in E. So the separable closure of F in E is E sub sep, the set of all the elements that have a separable minimal polynomial. Okay, so let's go into the proof. So again, the important part, as we will see, is to show that E sub sep is a field, is a subfield, and then it is to prove that for every alpha, I can raise it to some power of p and end up being inside this particular subfield, E sub sep, the separable closure of F inside E. Let's start with showing why it is a subfield. So what does that mean? I have to pick two elements inside this set, and then I have to argue that when I add them or subtract them, and when I multiply them, I will be still inside the same set. And if I give you some elements inside this set that is not 0, then its inverse is also inside this set. These are the statements that I need to prove. So it has some similarities with the proof that when I put all the algebraic elements together inside some arbitrary field extension, I end up getting a subfield. So meaning, I am going to look at alpha and beta. Then I look at the minimal polynomial of alpha over f. I look at the minimal polynomial of beta over f. By definition, both of these polynomials are separable. And therefore, the polynomial that's the product of them is also a separable polynomial. And now I want to consider the splitting field of f and argue that it is therefore a Galois extension. But let's, I have to do it in a careful way. So let L be a splitting field of f. As always, I want to still have alpha and beta in my disposal, even though my polynomial belongs inside f bracket x, and I want to consider the splitting field over f. But first I start with allowing this larger elements alpha and beta to be in the base field as well, and then relax it and argue that I'm going to get the same splitting field even if I change my base field. Again, the whole point is that I want to have the same alpha and beta inside my splitting field. So again, let's go to the details of the argument. Suppose L is a splitting field of the polynomial, that's the product of these minimal polynomials, over the base field that contains f, alpha, and beta. After all, I want to work with alpha plus beta, alpha minus beta. So alpha and beta are extremely crucial for me. I don't want to lose them. I want to have them inside my splitting field. So I look at my splitting field of this polynomial, that's the product of the minimal polynomials, over this base field. What is the base field? F square bracket alpha and beta. Now, notice alpha and beta, both of them, are zeros of the polynomial f. So if I add zeros of the polynomial f to the base field capital F, I'm already adding alpha and beta to it. Now, if I add other zeros as well, by this statement over here, I know I'm going to get the entire L. So L can be generated by this guy and the other zeros of F. But alpha and beta are also zeros of F. So L is generated by capital F and zeros of F, because alpha and beta are also there. That means L is also a splitting field of the same polynomial over capital F. You see, this part of this type of argument is technical, but we've seen this type of argument again and again. So the point is that we always start with a slightly larger base field to guarantee existence of certain elements inside my splitting field, and then argue that in fact I can relax my base field and make it smaller and get this and say that the splitting field is still a splitting field of the same polynomial over a smaller base field. Okay, we've seen this when we wanted to discuss normal closure and many other results of this type. Okay, so L is a splitting field of the separable polynomial small f over the field capital. It's a splitting field of a separable polynomial. And so L over f is a finite Galois extension. So remember, a splitting field of any field is a normal extension. Splitting field of a separable polynomial is a Galois extension. So L over f is a finite Galois extension. That implies, so what does it imply? That implies that every minimal polynomial, in particular, when it's a Galois extension, it's a separable extension, right? So every theta that I give you, the minimal polynomial of theta over f is a separable polynomial. Every theta inside L has a separable minimal polynomial. L contains alpha and beta. So it does contain alpha plus minus beta. It does contain alpha times beta. It does contain alpha inverse, considering the alpha is if alpha is not 0. All of these elements are inside L. But whenever I give you an element that's inside L, the minimal polynomial is going to be separable. So that means all of these elements, alpha plus minus beta, alpha times beta, alpha inverse, all of these elements have minimal polynomials that are separable, which means all of them belong to E sub sep. So E sub sep is indeed a subfield of E. Now, if I give you some elements inside F, the minimal polynomial of A over F is the degree 1 polynomial x minus A. It has only one zero, so it's clearly separable. That means that every element inside the base field F is already inside E sub sep. Altogether, we get that E sub sep is an intermediate subfield. So it's an intermediate subfield of so this is an intermediate subfield of E over F. Now this part is clear that E sep over F is a separable extension, as I've explained. This part is clear. And similarly, this part we have discussed it many times, that when characteristic is 0, every irreducible polynomial is separable, and therefore the extension is a separable extension, and so this equality is okay. Now let's go to the other non-trivial part of the argument. The other non-trivial part of the argument is when the characteristic is a positive characteristic, is P. In that case, the minimal polynomial of alpha over F is irreducible. Now, remember what we have proved about irreducible polynomials over here. We showed that if I give you an irreducible polynomial, then it has a separable form. You can find some G0 that is both irreducible and separable, and my original polynomial is just this G0 evaluated at x to the p to the m. Now, that means, you see, this minimal polynomial now is irreducible, so it has a separable form. Let's call the separable form to be, where is it? Yeah, so let's call the separable form to be S sub alpha comma F. So this is a polynomial in F bracket X with the following properties: that it is irreducible and separable. And what is the connection with the minimal polynomial? The minimal polynomial is S sub alpha comma F evaluated at x to power p to the k. Now, if I plug in alpha into this, I get that S sub alpha evaluated at alpha to power p to the k is the minimal polynomial of alpha evaluated at alpha, which is 0. So this means this polynomial, this means alpha at alpha raised to power p to the k is a 0 of this monic irreducible polynomial in F brackets. It is monic because M is monic. The M sub alpha is monic. That implies that it is a monic irreducible polynomial inside F. We know that when I give you a monic irreducible polynomial and I give you 0 of this monic irreducible polynomial, then this monic irreducible polynomial is the minimal polynomial of this element. So the minimal polynomial of alpha raised to power p to the k over F is this polynomial S of alpha comma F. But S of alpha, S sub alpha comma F is a separable polynomial, which implies that alpha raised to power p to the k has a minimal polynomial that is separable. So alpha raised to power p to the k belongs to the separable closure of F inside E. This completes the proof. This shows that an arbitrary element alpha inside this field can be raised to some power of p, end up being in the separable closure of F inside. Okay, so I stop here. We continue using this in the next lecture to study tower of separable extensions and purely inseparable.